There, welcome to the second video on our rates of reaction. Now this one's going to deal more with rate determining steps, okay, and things like that. Determining steps, and we get these from the rate equation. Okay, now to be honest with you, it's quite a hard concept, so I think the best thing to do is do it by an example that you all know. And I'm going to look at the hydrolysis of a primary halogenoalkane. Okay, and then I'm going to look at a secondary, or probably not a secondary actually, just to make it more clear, let's do a tertiary. And then I'm going to look at a tertiary halogenoalkane. Okay, so I'm going to look at the hydrolysis of that now, and I'll use those examples to try and explain the rate determining step that we talk about. Okay, so first of all, let's do a very simple one. Let's have a look at this guy here. And this guy is going to be called This is chloroethane. And I'm going to react it with sodium hydroxide. Okay, this is AS stuff. And it is a nucleophilic substitution reaction. And I'm going to end up with ethanol and sodium chloride. All right, so what's going on? If you remember your chemistry, let's have a look. Let's draw the mechanism. I know you know all of this, but hopefully it will help. All right, first of all, we have to draw our charges. So that's delta positive, delta negative. And our nucleophile is going to be the OH minus ion there with its negative charge. It's going to attack this positive here. And at the same time, these electrons are going to go over here, and we're going to get basically this, aren't we? We're going to get our product. Okay, what color was that? That was blue. The OH has gone on, and the Cl has come off. Okay, all right, and this is a nucleophilic substitution reaction that we all know and love. Now, if you do the kinetics for this reaction, if I did this and I kept the halogenoalkane constant, so let's call this CH3, CH2Cl. If we keep this constant in my reaction, and I do that by making it a large excess, okay, and I let the concentration of my hydroxide ions change. All right, this is going to vary. Okay, now if you've seen the last video, we draw a graph. Okay, and we draw a graph of the concentration of the hydroxide ions against time. Okay, and we'd see it dropping off against time. And then we'd use that graph. If you watch the previous video, you'll know what I'm talking about. We use that graph to create a further graph, and the further graph, or the second graph, is the rate against the concentration of hydroxide ions. And you would get, hopefully, you would get a straight line. Okay, so you can say the rate is equal to some constant times the concentration of hydroxide ions. Okay, now you'll have to have seen the first video to understand this very quickly anyway. So you get the rate is equal to some constant times the concentration of hydroxide ions. So already we know the reaction is first order with respect to hydroxide ions. All right. Now we do exactly the same, but we, in the second case, here we go. This is our second experiment. In the second experiment, what we do is we keep the concentration of hydroxide ion constant, and we change the concentration of the halogenoalkane. Okay, this can vary. And we do everything again. Sorry to repeat myself all the time. But we do the first graph, it's going to be something like that. Second graph is going to be like that. Okay, and the second graph, if you remember, is rate against concentration. And in this case, it's the concentration of the halogenoalkane. Okay, so from the second one, we can say the rate is equal to some constant times the concentration of halogenoalkane Okay, I'm going to call this rate K1, K2. And then we can combine these and we can get an overall rate equation. Okay. And the overall rate equation is R is equal to K into the concentration of the halogen alkane times the concentration of hydroxide ions. Okay, now as you can see, it's first order with respect to the halogenoalkane. Let me move the paper up a bit. It's not really paper, but you know what I mean. And it's also first order with respect to the hydroxide ions. Okay, and as you can see, overall, the order is 1 plus 1 is 2. And that's why, by the way, this mechanism is known as an SN2 mechanism, because that 2 is that 2. All right, that's why we call it an SN2, because the rate determining step has 2 molecules involved in it. And the rate determining step, the slow part of this reaction, was, well, there's only one part of the reaction, if you like. There's only one step. As this goes on, as the OH minus goes on, this Cl comes off. So it's a one-step reaction. It's a one-step reaction, all right? And I don't know if you know you remember your AS. If you were to do a reaction profile, it would look like something like this. This is my energy. And it would look like this, there and there. And you just get one step. This is a one-step process. These are the reactants, these are the products, and this is the transition state up here. All right, there you go. All right, so this is a one-step reaction. Two things are involved, two concentrations are involved in the slow part of the reaction, and we can see both of those in the rate determining step. So here, this is involved, and here. I vary one, the rate will change. I vary the other, the rate will change. Okay, so let's compare that to a tertiary. Okay, so we're going to do exactly the same. We're going to, well, not exactly the same, but this is now the hydrolysis of a tertiary halogenoalkane. Halogenoalkane. All right, and the one I'm going to pick is this one. I'm going to say CH3, 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 and then Cl. All right. Now, let me get my red. Oh no, let me first of all do the equation and then do it nicer. We're going to react this with sodium hydroxide, and we're going to get. Well, if you start off with a tertiary halogenoalkane, you're obviously going to get a tertiary alcohol at the other side, aren't you? And we're going to get sodium chloride there. What's the mechanism? Well, all of you should know this, but let's just say CH3, 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 Cl. Let me do my differential charges, delta plus and delta minus. Now, believe it or not, the first step of the reaction, of this reaction, is actually these electrons going onto there. So the first step of this reaction doesn't have anything to do with the hydroxide ions. It's bizarre, but that's the way it is. All right, and now that's going to give me, it gives me the carbocation, which is CH3, 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 and let me do my charges in red. It's going to be plus, and what's fallen off? The Cl minus has fallen off. There you go with its electrons. And in the second stage, let me do this in green. My OH ions in a second stage will now, oh, I need a different color. All right, I'm going to pick this white color. This will attack this. So this is the second stage of the reaction to produce my product, which is, I'm going to draw this quickly, I hope you don't mind, CH33COH. Okay, so let me draw that again. The first stage of the reaction is this. It's CH3CCl goes to CH3, 3C plus, and Cl minus. And the second stage of the reaction is CH3, 3C plus, plus my OH minus ion gives me CH3, 3COH. Oh, I think that's it. No, it's gone too far there. Now, there's two steps here. There are two steps to this equation or this reaction, two mechanistic steps. One of them is faster than the other one. Okay. Now the fast one, well, this one looks fast to me. Before we look at it, this one looks fast because you have a positive thing reacting with a negative thing. That's always quite fast. Okay. Now the first part, the breaking of the CCl bond, is quite slow. Okay, so there are two parts to this, and one is slow and one is fast. And it's the slow one that determines the rate of reaction. Because, believe it or not, however quick the quick one is, things will only take as long as it takes as long for the slow one to happen. Okay, if you can think of a race, 10 people in a race, the race starts and the race finishes. When does the race finish? The race finishes when the last person crosses the line. The first person might do the 100 meters in 10 seconds, okay? And the race is finished for that person, but the overall race hasn't finished. The overall race finishes when the last person crosses the line, the slowest person crosses the line. So we call the slowest part of the chemical reaction, the one that determines the rate, is known as the rate determining step, okay, which I'm sure you've all heard of. Now, if the rate determining step is what determines the speed of the reaction, the rate determining step species, the chemical reactants in the rate determining step, must appear in the rate equation, because the rate equation tells us about the rate, and therefore the slow things are the things that tell us about the rate. So therefore the RDS, the rate determining step, determines what species. And now we use this term, I hope you're familiar with it, but species is just a chemical thing, like an OH minus ion is a species, or a CH3Cl. Well, there should be a 3 there, shouldn't there? That's a species as well. But the rate determining step determines what species appears in the rate equation. Okay, there you go. So let's have a look. Well, this is the rate determining step, this one, and there's only one thing in there. So in this case, the rate equation will be this, won't it? R will be equal to the rate constant into CH3, whoopsie daisy, CH3 3 times, CCl, and that's it. Okay, and as you can see, this is order 1, okay, and that's why the overall order is equal to 1, and that's why this mechanism is known as an SN1, because overall it is order 1. Okay, but it's only the rate determining species that appear in the rate equation. I think you understand that. Okay, so now what I'm going to do, I'm going to do a couple of examples. Okay, I think that's the best way to do it now. All right, this first example, if I can copy this and paste it here. There you go. I just do a nice equation here. All right, now I really would hope and expect that if you don't understand this video, you'll get back to me, because it's very important that you understand this. All right, so here we go. Ethanol dimerizes in alkaline solution according to that equation. The initial rate of the equation was measured, starting with different concentrations of the ethanol and the OH minus ions. The following results were obtained. There you go. Deduce the order of reaction with respect to the ethanol. All right, this is the ethanol. Let me get a nice red pen. This is the ethanol. So I've doubled my ethanol concentration, and I've doubled the rate. Okay, so therefore it must be first order. I've doubled one, the other one's doubled. So with respect to the ethanol, it is first order. Okay, with respect to the ethanol. Deduce the order with respect to the OH minus ions. Now, let's have a look at this. Well, I'm going to pick this one and this one. Okay, this is doubling. I'm doubling the OH minus ion concentration, and I'm timesing this one by 4. So this is times 2, and this is times 4. Okay, so 1 times it by 4, and and the OH minus I'm timesing by 2 to get a new one. Now the rate changes by a factor of 8. Okay, so the contribution of the ethanol is a times 4ing of the rate. Therefore, because the overall rate changes by times 8, the contribution by the OH minus must be times 2. So I've times the concentration of OH minus ions by 2, and therefore its contribution to the rate must have also been times 2. All right, if you don't understand that, I'll do more on that if you don't understand. So deduce the order of reaction with respect to OH minus, and it is first order with respect to OH minus ion. Therefore, give the rate equation. Well, the rate is equal to some constant times the CH3, CHO, times the OH minus ion. There we are. Okay, and that's that one done. Often then they'll ask us to state the rates, the units of the rate equation, and they do here. You'll see in a minute once I manage to paste it on. If I can, here we go. All right, there we are. And the first thing it's done is asked us to, right, first thing it does, it asks us to state the units of the rate equation. This is how I do this, okay? The K, I'm going to write on here, but I'm going to rub it out in a minute. All right, so I say the constant from this equation here is equal to the rate, and the rate has units moles per decimeters cubed per second, and we divide that by concentration, moles per decimeter cubed, times concentration, moles per decimeter cubed. One of those cancels out with one of those to give me per second is on the top. Moles, there's a nasty little dot there that looks like minus, but it's not. Moles has to come up at the top, so that becomes moles to the minus 1. Decimeters to the minus 3 must come up, so that becomes decimeters cubed. Okay, so they're the units of the rate constant. So moles per minus 1, decimeters cubed per second. All right, that's how I do that. Now, let's get rid of all this stuff. All right, this isn't the hard part of the question. It's coming up in a minute. Calculate the initial rate of reaction, the relative value, for a reaction where that is 0.3 and the OH is 0.3 as well. So I can't remember the numbers. So let's have a look then. If it's, as you can see, where's my pen again? All right, so I'm going for, if you look up here, 0.1 to 0.3 is going to times it by a factor of 3. So my rates, okay, let me do this. If it's 0.1 for the concentration of the ethanol times 0.015, this equals 1, okay? And that's from the first row above. First row from the table above, okay? So now, what have I got to do? I'm looking at this, 0.03. All right, so if I change this to 0.3, okay, that's going to times it by 3. And then I'm going to change this to 0.03. That's a timesing by 2, isn't it? So I'm timesing this by 3, timesing this by 2. So it's times 3 times 2. So the relative rate is going to be 6, okay, if we do that. Okay, so that's the answer to that one. So there's the relative rate here. If I change the OH from 0.013 to 0.03, it's going to change it by a factor of 2. And if I change it from 0.1, the ethanol, to 0.3, that's going to change it by a factor of 3. So one of them is going to change it by a factor of 3. The other one is going to change it by a factor of 2. Therefore, the overall change is a factor of 6. Okay, I hope that makes sense. If it doesn't, please get back to me. Okay, now, whoopsie daisy, where are we? We've done that one. Now, this is the interesting bit, I think. Maybe, let's see. I'm going to paste this there, make this bigger. All right, there we are, a bit smaller. All right, a three-step mechanism has been proposed for the reaction. Okay, and there it is. Using your rate equation, predict which is the rate determining step. Okay, so let's have a look at them all. All right, if this was the rate determining step, if this was the rate determining step, and if this was the rate determining step. Let's work out the rate equations for all three. Okay, now let's have a different color. Let's not be green. So let's have a look. The rate would be equal to some constant. The rate would be equal to some constant. And the rate would be equal to some constant. Times what? Well, if it were this one, it would be the concentration of this times the concentration of this. Now that, to be honest with you, looks like the answer already. CH3, CHO times the OH minus. And that's what we got. So this, with the information we've been given, is the answer. So the answer, the rate determining step is step 1. And the explanation, because the reagents fit with the rate equation. Okay. All right. Now, it doesn't seem like a very satisfactory answer there, does it? And I'm sure I could make that better. But if you want to look this question up, I think it's 2017, you might see a better answer there. All right. But let me try and do it better. Actually, I think I've got the answers here. Let me see what the answers say. Right. Winter 17, is that it? B. Let's have a look at B. That's not the right one. Let's have a look at this one. B. No, it's not that one either. So it must have been an older one. Anyway, so why is the rate determining step step A? Well, because it contains one molecule of ethanol and one molecule, if you like, of OH minus ions. And that fits the rate equation. All right. Let's say it's number 2. What if it was this one, though? What would the rate equation be for this one? Well, this is a good exercise. So if it was number 2, well, there's one of these here. Okay, so we have to put one of those in, CH3, CHO. And there's one of those, so it's power 1. Okay, now there's none of these. Okay, all right, we haven't got any of those. That's not a reagent, is it? So we have to, where did this come from? Well, this came from there. Okay, and how did we make this? Well, we made this with one of those and one of those. So that means to make this, we have to have one of these and one of these. So they must go in the rate equation as well. So there's one. But now there's another one of these things. So this must change to order 2 now. We didn't see that, so that can't be the answer. So it's not the right answer, but this would be the rate equation if step 2 were correct. Let's have a look at step 3 now. Oh my word, what on earth is this thing? So let's have a look at this. This would be, well, I can't find this anywhere, but how do I make this? I make this from this one. And how do I make this? I make it from this and this. So if it was this one, okay, the rate would be one of those and one of those. So it would be CH3, CHO. All right. And now I've got to make this again. And how do I make this? It would be one of those and one of those. So that would be squared again. And this would be OH minus. Okay. Now that's how we make this thing. But also water is there as well. So we'd also get water in the rate equation. All right. Obviously, step 2 and step 3 aren't the answers for us. Step 1 is. But I'm just showing how you build the rate equation given the steps. Describe the chemical behavior of CH3, CHO in step 1. CH3, CHO in step 1 is, well, it's attacking the negativeness, so it's acting as an electrophile, isn't it? All right. So I think that's what we want now. It's because it's attacking my OH minus. That's negative, so it's attacking there. Name the mechanism occurring in step 2 and step 3. Right, what have we got there? Step 2 and step 3, they're coming together, and water is coming off, and a small thing is coming off there. So what happens here? Well, I'm trying to look this. This forms a bond here. Okay, and these electrons go up to here. So this thing here is acting as a nucleophile because it's attacking this. So it's nucleophilic. Okay, and it jumps on there to form this. And then what happens here? Acts with water. I'd say this is a nucleophilic elimination reaction. Okay, but that's not really why we're here. But it's all good stuff, isn't it? Right. So let's go to the next one. All right. I think is that it. Now the last bit here. Okay. Oops. There's it. We'll copy this, paste it here, and open this out. There we are. Using diagram below, show the mechanism for step 2. All right. Step 2, I think I've accidentally done that already. What was step 2? Step 2 is that, yeah. I've kind of done this, haven't I? So what do we get? We get that. There you go. All right. So let's write in our charges. This is delta plus, and this is delta minus. So these electrons here attack here, and these electrons go up to here, and these two things form. When these form, you get CH3, you get the O minus up here with the electrons, you get the H here, you get a bond formed here, you have CH2 here, COH, and there you go. That's what's happening there. All right. Now, I don't know how long the video's been going, but I don't want to make it too long. Let's have a look. There's a very similar one to come, but there's another one I wanted to show. Okay. Right, this one at the bottom here. I do apologize if we're going on too long. Right, let me see if I can do it there. Yeah. All right, let's try and do this one, and then you can argue with me if you don't agree with anything, which is a good thing. Oops, wrong thing. There we are there. So let's copy this. Let's paste it here. There it is. It looks very similar, doesn't it? All right, what do we mean by the order of reaction? The order of reaction is the power to which the concentration term is raised in the rate equation. Okay, that's what we mean by order of reaction. It's the power you have to raise it to. Okay, right, let's move down. Okay, a lot of calculations here. I didn't expect this, but never mind. Let's move this up and paste another one. Alrighty, and now I obviously need the things from above. Use the results of experiment 1 to calculate the rate constant for this reaction, including the units. Okay, so which is experiment 1. Use experiment 1. So experiment 1. Do we know the rate constants here? Hold on, I think I'm rushing this. The rate of reaction is measured at various concentrations, and the following results were obtained. There you go. Oh, there we go. That's what I was looking for. I was looking for the rate equation. We don't have to work it out. Right. So use the experiments there. So we've got to find K here. So K is equal to the rate, and the rate is 7.04 times 10 to the minus 3 divided by the concentration of sorry, I'm using the wrong one. That's what happens when you rush, I'm afraid. I didn't want this video to be this long. All right, so we're using experiment 1, aren't we? So it's 2.20 times 10 to the minus 3. That's the rate, divided by 0.01 times 0.06. I don't know what that gives me, and I'm not that bothered, really. You can work that out. The next one, the initial rate is that. I'm not going to bother with that either. And experiment 3. If you have a problem with these, ask me and I'll do them for you. But what do we mean by the rate determining step? That's the slowest part of the reaction. All right. Now I wanted this last bit in because this is what Marco specifically asked about how you put things in here. So let's have a look at this one. The equation for the reaction between that and that is that. Now, the mechanism has two steps. Suggest equations for the two steps of this mechanism, stating which of the steps is the rate determining. So there's two steps involved in this. Okay, and one of the steps must involve one of these plus one of these forming something. That's one step, and the second step is something else. Okay, so which one is the rate determining step? It must be this one with one of these in and one of these in. So let me try and show you what I mean. I don't know what the mechanism of this is, but I'm just going to guess. Okay, so I'm going to say the first step is one of these molecules reacts with one of these. What does it form? I have no idea what it forms. I'm going to say they create some sort of bigger molecule. Okay, there. I don't know if this is true, but it suggests. So it doesn't have to be right. It has to just fit the information available. So one of those joins with one of those, and we get one of those. All right, let me cover this. Now, since this step is the one that has the molecules in the rate equation, this must be the rate determining step. So I'm going to say the rate determining step is step 1. Step 2, well, obviously this character here must die somehow. All right, so it's got to cancel out in step 2. So let me draw it first of all in step 2, ClO, F2. Now it's got to react with the other one of these because I've only used one of those up, but two of them are involved in the equation. So let me use the other one up, ClO2, and now it's got to give the product, doesn't it? 2Cl that. Okay. Now there's an F there, and that's F2. All right. Now, why is this an acceptable answer? Well, if you add these two together, this will cancel out with that, and I'll end up, if we add these steps up, you've got to end up with that, and we do if we add these two together. All right. By considering the rate equation, explain why the rate increases with increasing temperature. Well, if you think about it, if you're looking at the rate equation, if you increase the temperature, you get a more frequent particle collisions. Okay, there you go, looking at the rate equation. And also, if I consider explain the rate increases with increasing temperature, also K, well, the rate constant will increase with increased temperature. Okay, that's always the case, by the way. Okay, the rate constant K increases with increasing temp. All right, now I'm sorry if I've missed any bits and pieces out here. I've tried to rush this a bit too much, but please do me a huge favor. And if you don't understand something, just ask, okay? And I'll promise you I'll correct any mistakes I've made in this video. Okay, bye-bye.